Hi everybody, I'm Razvi. Welcome back again to pwn101 series, where we are solving the pwn101 beginner level binary exploitation room from TryHackMe. In this video, we are solving the fourth binary. I've downloaded the binary and now let us check what kind of protections this binary has been compiled with. This binary has no stack canaries, which allows us to perform buffer overflows without worrying about the binary detecting the stack smashing. The NX bit, non-executable bit, is disabled, which allows us to execute code or shellcode from the stack or heap in case we need to. And we can see it isn't a position-independent executable or code, which implies that the addresses of the binary itself, the addresses of the text memory segment where the code resides, won't change between executions. As we can see, this binary has no protections at all. Basically, it is vulnerable to pretty much everything. Okay, so let us now execute it to see what it actually does. I think I have some superpowers, especially executable powers. Can we go for a fight? I'm waiting at, and the binary is printing a given address. Let's see if it is vulnerable to format string vulnerabilities. It isn't. Let us execute it again and maybe test a huge input. And we got a segmentation fault, which means that somewhere, at some point, the binary is vulnerable to a buffer overflow attack. We are able to corrupt memory, and the binary tried to return to an address we just overwrote, with of course just A's, which aren't a valid address. That's why we are getting a segmentation fault. Now let us take a look at the address that the binary is printing. As you can see, it changes between executions, but the first bytes seem to be the same. Now, the more experienced viewers may already identify this as a stack address, which gives a clue about what this binary is all about. In case you don't, do not worry, because I'll guide you through the process and you may soon find out why this is necessary. Let us execute the binary one more time and see that it indeed changes once again. If we execute it again, the address will of course be different. Now, what is this number and why does it change with every single execution? Is it a random number that the program is computing? As I've already said, it is a stack address. The binary is leaking a stack address and it changes with every single execution because ASLR, which stands for Address Space Layout Randomization, is enabled in my system. We can also see how ASLR randomizes addresses by executing the dynamic linker on the binary and taking a look at, for example, the base address where libraries are loaded with every single execution, in this case, libc. As you can see, every time I'm invoking the dynamic linker, the address is different from the previous ones. Now, what is this address space layout randomization thing? It is a system-wide protection or defense mechanism that randomizes addresses of several memory segments, for example, the heap and the stack, whose main purpose is making difficult the exploitation of several vulnerabilities like the buffer overflows in order to execute shellcode, or difficulting the execution of return-oriented programming attacks. Now, I won't go very deep into what ASLR is because that's not the purpose of this video, but I will of course give you some resources in case you are curious about how does it work, what it is, and how you can abuse it, how you can bypass it. When you Google ASLR, you can see that Google already highlights the IBM entry for this protection, which states that it is a technique that is used to increase the difficulty of performing a buffer overflow attack that requires the attacker to know the location of an executable in memory. Let us take a look at Wikipedia's page about ASLR, which is surprisingly good. Now, the Wikipedia states that address space layout randomization is a computer security technique involved in preventing exploitation of memory corruption vulnerabilities. In order to prevent an attacker from reliably jumping to, for example, a particular exploited function in memory, ASLR randomly arranges the address space positions of key data areas of a process, including the base of the executable and the positions of the stack, heap, and libraries. So basically, it is thanks to ASLR that addresses change between executions. Now, there is a pretty interesting paper called Exploiting ASLR Weaknesses, which I'll leave in the description and maybe we can discuss in the future. But for now, I just recommend you reading it if you want to know more about ASLR, how does it work, and how you can bypass and exploit it. For example, it is very interesting how in 32-bit operating systems like Linux, the entropy is just 8 bits. As you can see in this diagram, the actual bits that are randomized from a given 32-bit address correspond to just the high nibble of the second byte and the lower nibble of the third byte. That means that even though ASLR is enabled on a 32-bit operating system, the higher byte and the lower byte of the address will remain the same, and also their respective contiguous nibbles. In other words, since only 8 bits are randomized, as you may already know, with 8 bits, which is a byte, the possible values we can represent go from 0 to 255, which is a very doable attack from a brute force perspective. This low entropy makes brute forcing attacks feasible, viable. As it states in the paper, the lower part of the address is not randomized due to page alignment, and the upper part is not randomized in order to avoid fragmentation. This is a very interesting and elucidating paper which I recommend you reading. Now you could of course disable ASLR in your system, but I don't recommend you doing so. It is good from a learning perspective, as a learning exercise, it might be good, but it is unreal. Nowadays, systems have ASLR enabled by default. We are not living in the 90s anymore. I won't say it is impossible because you never know, but it is uncommon. You will hardly ever find a system without ASLR. So if you are learning binary exploitation, I recommend you doing so with ASLR enabled. Okay, now back to our binary, let us debug it as always. Okay, let us now take a look at the assembly of this binary. Let us reverse it. We can see that at a first glance there are no interesting functions, at least declared. So let us start from the very beginning, from the main. The main function is actually pretty small, and there is a call to setup, to banner, which aren't of our concern, several puts, and then a call to printf that prints the string I'm waiting for you at and the given format specifier, and then there is a call to read. Read is a function that basically reads bytes and stores them into a given buffer without caring about their format. It simply reads bytes. As we can see from the corresponding Linux man page, read attempts to read up to count bytes from the file descriptor fd into the buffer starting at buff. In our case, it reads from the file descriptor 0, that is the standard input from our terminal, up to 200 bytes, or C8 in hexadecimal, into the buffer buff, which leaves at RBP -50. The read function isn't a vulnerable function per se. In this case, the vulnerability is self-induced. It was induced by the programmer. They weren't careful enough and they allocated 50 in hexadecimal or 80 bytes for this particular buffer, and they are attempting to write up to 200 bytes. Of course, there is a buffer overflow which we can abuse. Now the thing is, okay, we have seen in previous videos that we can modify memory with arbitrary values, we can jump to functions, we can hijack the execution flow, but in this case there is no function that we can jump to. How can we spawn a shell? We could of course take a look at the disassembly perspective menu view from Cutter, because sometimes functions are just hidden in the code. The graph view tries to parse functions, that is, functions that start with the function's prologue and end with its epilogue. But there could be code in our binary that doesn't necessarily start with an epilogue, for example. We could of course start taking a look and searching for functions, but believe me, there is nothing for us to execute. There is no way in this binary from its original code that we can spawn a shell. So how can we do that? Is it even possible? Well, let me tell you, it is indeed possible. As we have seen, this binary has the NX bit disabled, that is, we can execute code from the stack. And what data is being saved into the stack? What is written in the stack? our provided data, the user's input. So what is preventing us from providing bytes that correspond to actual instructions as input and somehow manage to execute them? Well, since this binary has no protections at all, there is nothing preventing us from doing so. And that's indeed what we are about to do. And with that being said, enter shellcode. Shellcode nowadays is a very general term that is used to define any single piece of arbitrary code or payload that we can execute by abusing a given vulnerability in a binary. It is called shellcode because historically it was used to start a command shell, to spawn a shell on the victim's machine. But nowadays it is used to define any single piece of code. In fact, it is very common to see shellcodes that spawn a calculator, especially in proof of concepts, because it is generally considered that if you manage to spawn a calculator process by abusing any other process, it means that you're able to perform arbitrary code execution. In other words, you successfully exploited the binary you were trying to abuse. Okay, so let us recap for a moment. We have seen that we can abuse the read call from our main in order to perform a buffer overflow and write into memory a shellcode, and we can somehow execute this code. There are two questions that we must solve now. First, how do we get to execute the code we are providing as input? And second, what is our input? What are the bytes or what is the shellcode that we must provide the program with? Well, for the first question, we must take into account that, as we have previously discussed, ASLR is enabled in the system, so our stack addresses will change between executions. And how do we know, or why do we care about a stack address? Well, basically because our input is saved into buffer, which is a variable, a buffer that is stored in the stack. It is local to this function, to the main function. So, in other words, we need to know where our buffer is, its actual address during a given execution, to be able to return to that address. Since we are able to exploit this buffer overflow, we can manage to hijack this program's execution flow by overwriting the main return address, and instead of jumping to any given function as we did in the previous video, we will jump straight to our shellcode. Now, how can we know the address of our buffer during the execution? How can we leak its address? In this case, it is very simple because the author of the room is by our side and we are learning how to do so. If you remember, when we execute a binary, we get printed an address. And what is this address the binary is printing? As you can see, printf takes the address of buffer and it is parsing it, it is printing it with the p format specifier. In fact, we can take a look at this very address where this string is living to see what it is all about. And we can see it corresponds to the p format specifier. And what is this format specifier? Well, if we take a look at the documentation of the printf function, we can see that p stands for a pointer address. In other words, is printing the address of the buffer itself. So the address the binary is leaking, the binary is printing, with every single execution corresponds to the address of the buffer where our input will be stored. So now, all of a sudden, we know where we have to jump to in order to execute our shellcode. That is, we know what address we have to overwrite the main's return address with. And now there is only one remaining question for us to answer, and that is, what is our input? What is the shellcode we must provide our binary with in order to later execute it? Well, we could basically develop our own shellcode. While it's true that shellcoding is very fun and very profitable as to gain knowledge about how computers work, it isn't the purpose of this video. Since we won't develop our own shellcode, we will of course take one from the internet, which is already prepared to be used as payload in our exploit. First of all, we have to consider the architecture. In our case, it is a 64-bit executable, so we are looking for a shellcode that works for 64-bit operating systems. In our case, it is a Linux. Now, when you are looking for shellcodes on the internet, there are tons of sites that provide you with already prepared shellcodes that you can execute. However, the reference sites are always Shellstorm exploitDB, and packet storm security. You can use whichever you like the most, they work just as good. I'll be using this one from exploitDB. As you can see by its title, it is a shellcode which is 23 bytes long and works for Linux 64 bits, and it executes execv passing as a parameter the bin.sh string, which of course is a call that spawns a process corresponding to a shell. Here in our code we can see it is describing the instructions, the assembly it is executing, and we are provided with this string of bytes. This is our input, this is our shellcode. That's what we should care about. As you can see, here are the instructions this shellcode is executing, and these are its corresponding bytes, the corresponding opcodes of every given instruction and its arguments, its parameters. See how these opcodes are indeed the bytes we are providing the binary with, and they will be placed in memory just in the correct format for its execution. So now let us go ahead and prepare our exploit. I will copy the shellcode. And finally, before writing our exploit and testing it, you have to bear in mind that if your intention is to debug the shellcode or to test the shellcode in your local machine, you have to look for a shellcode that works for your given architecture, for the architecture your operating system is working with. If you were to try this shellcode in a 32-bit machine, it won't work, because as you can see, it is using 64-bit registers. In that case, you would have to look for a shellcode that works in 32-bit machine, for a 86 shellcode, which could be this one, for example. Okay, so now let us write our exploit. So let us recap for a moment. We are launching our process, we are parsing its output, we are storing it into a variable that we later work with. In this case, we are splitting the output by the @bytes sequence because we want to split them by this byte sequence, and we are retrieving just the second result from the array because the first result will be all this output, and we are just working with this second substring or token. We are of course stripping it, we want to get rid of white spaces, and we are decoding as UTF-8 because we don't want to work with bytes, we want to work with actual strings. And finally, we are converting it into an integer and we are parsing it from a hexadecimal base number. This way we can get the address of our buffer. Now, what are we writing in our buffer? We are of course writing our shellcode that we got from exploitDB, and we are padding the remaining space with enough bytes to reach RBP. That is 50 in hexadecimal minus of course the length of what we have already wrote, which is the shellcode of course. 8 more bytes to overwrite RBP itself, and finally the address of our shellcode. We send the payload and then we spawn an interactive session. And now let us test it to see if it actually works. I got an error that says I can only concatenate string to string, not bytes, and that's because I forgot to place the byte specifier in front of our shellcode. I must of course specify that I want the shellcode to be interpreted as bytes, not as a literal string. And now, as you can see, I got the shell. So we have successfully exploited the binary locally. Let us test it remotely. So I have changed our exploit to execute the process remotely at a given IP and port, and let us execute it. Let me clean the screen first. As you can see, I got a list index out of range error, and this is a very common error because sometimes the output a given binary generates locally differs a little bit of what it generates remotely, because over the network sometimes bytes get interpreted slightly different. What I mean is that maybe remotely the output of the binary is split into several messages and we are receiving just the first of them. How can we debug, how can we detect this behavior or these errors? By specifying the log level variable of the context environment to debug. This way, when we execute the exploit, we can see what is being received over the network. As you can see, what we received with our receive call, this one right here, is just these bytes that correspond to the banner of the binary. We didn't receive the address that the binary is leaking. How can we solve that? Well, just as simple as executing another receive and saving the output of just the second one. As you can see now, we received the first message, which corresponds to the banner that we don't really care about, and then we received the second output, which is where our address, our leaked address is. And this is the one that we parsed, we interpreted, and then we sent our payload back to the program. And now, as you can see, we are using a shell in the remote machine, in the victim's machine. Since we are in a debugging context, our pwn2shellcode exploit, the script we are executing, prints every sequence of bytes we are sending, and it prints back to us every single sequence of bytes we are receiving. But we don't really care, we can use our exploit just like that. As you can see, as always, there is the flag file that we can read, and let us check if the flag is actually correct. Which apparently it is. And that was the fourth binary from the pwn101 TryHackMe room. In this binary, we managed to successfully exploit a buffer overflow in order to hijack the program's execution flow and execute our own shellcode, the input that is being saved in the stack. I hope you liked the video and found it useful. If there's anything you want to say, leave a comment below. And remember, exploit code, not people. See you in the next one. Until then, GG.